Hello students, so this is the explanation video for this gear numerical. So here it is written that a pair of spar gears with 20-degree full depth involute teeth needs to be designed. So in general, in numericals we have three types of involute teeth, that is 20-degree full depth, 20-degree stub, and 14.5-degree full depth. So depending upon that, this type 20-degree full depth or 14.5-degree full depth or something, we have to decide something called Lewis form factor. Okay, Lewis form factor, we'll come to that actually. So these informations are important. So you see, the number of teeth in this pinion is 18. So this is also important, number of teeth in the pinion. Okay, so then speed ratio is 5:1 and the face width is 10 times the module. I mean this question is given to you. Okay, so I'll just explain this question, what are these things. Okay, first of all, in a gear drive, okay, we have two gears. I'm showing quickly. This is the smaller gear, we have a bigger gear mating with this. Okay, so the gear teeth are actually they are of this kind of shape. Okay, like this. Okay, in 3 dimension, if you see, then this surface is actually the involute surface, involute. Okay, so involute means here if we roll a line here, okay, then it will I mean involute is actually, you can say, if we roll a line over a circle like this, and if we mark a point here, then when you purely roll the line, then this point, the locus of this point, is called the involute. Okay, so here this is involute, and involute is actually provided in gear teeth just to reduce the, you can say, reduce the friction between the gear teeth. Okay, so that we have pure rolling between two mating teeth. Okay, so here you see, this smaller one is called pinion, you know, and bigger one is called gear. Okay, so pinion will have smaller, this diameter is more here lesser than gear, this diameter is more, so we just write dg for gear and dp for pinion. Okay, so now since it is smaller, so it will have less number of teeth than gear, so we just write zp to show number of teeth in zp for number of teeth in pinion, and zg for number of teeth in gear. Okay, and that if this pinion is rotating in this direction, the gear will rotate in the opposite direction. Okay, because you see, this is rotating in this direction, this will drive the gear in the opposite direction, this manner it will rotate. Okay, so now that its rpm, speed of pinion, we write it as small np, and speed rpm of gear is ng. So we have a relation between all these. This is called speed ratio. So speed ratio, if we write this, see, smaller one will rotate faster than the bigger one. So if the speed ratio is greater than 1, okay, that is, if we write, suppose speed ratio is 4:1 or 4 only, or 5:1 or 5, here it is given in this question, it is 5:1, that means it's greater than 1. 5:1 means 5 only. So that means this, you see, smaller one is rotating faster than bigger one, right? So that means this np is greater than ng. So since it is 5, if it is greater than 1, if you write, then this will be np by ng. Okay, speed of pinion is more than speed of gear, so this is np by ng, which is equal to inverse of the gear teeth, because you see, larger one will have slower speed. Okay, that's why this is inverse, and also larger one will have bigger diameter. So diameter is big, so number of teeth will also more, but its speed is less, that's why it is inversely proportional to speed. So dg by dp, this relation is called your speed ratio. Okay, and this is useful relation, so that, using this relation you can find out number of teeth, diameter, and speed. Okay, so now you have understood this. Now there are three types of gear teeth: 20-degree full depth, okay, full depth, 14.5 degree full depth, and 20 degree stub. So we do not solve numericals for this actually in this course, and we also, I have not included any numerical for 14.5 degree full depth. Numericals will have only full for 20 degree full depth gear teeth. Okay, I'll show you in the data book what, why, why this information is required. Okay, next is, okay, next, yeah, number of teeth in the pinion is given. Okay, speed ratios now you have understood is given. Face to width is 10 times the module. That means here you see this is the width. Okay, okay, width of this side, this is the width of the gear. Okay, and this is, so we face, so sorry, this is the width, this is the face. So face of the here is written is face width, the face width is 10 times model. So this is the face width, forget about this, this is the face width of the gear. So face width is written as B, and which is 10 times the module. Okay, 10 times the module. Okay, so here, I'm sorry, this is not the face width. Face width will be this one. Okay, this is P, which is given as 10 times module. Now okay, we'll come to this. Now module is a very important term in a gear. Okay, module is given by diameter of the gear divided by number of teeth. Okay, so from here you see, using a module you can design a gear. Okay, a proper module is very much important for designing of a gear. All right, okay, now you see, in gear design you have to actually decide the module. Okay, you are not, you are calculating the module, but we will see how to decide or how to estimate the module. Okay, we'll see that. So remember this relation, module is equal to D by Z. Okay, diameter, gear diameter divided by number of teeth in the gear. Okay, now you see, input shaft rotates at 800 rpm and receives 6 kilowatts per hour. Normally input, one of them will receive the power from any other source, maybe from your this one, it will receive power from motor or from any external source, and to deliver power to gear. Okay, so normally we provide power to pinion. Okay, so pinion input shaft here means pinion speed, input shaft rotates speed 800 rpm means this is NP is given 800. Okay, 800 rpm speed of pinion is given. Okay, and here you see it receives 6 kilowatt power. So also the power provided to this pinion is given. So power here is 6 kilowatt, which is useful in calculating the torque later. Okay, speed is known, power is known. From power is equal to torque mt multiplied by omega. Omega is nothing but 2 pi n by 60. So here you put this n, and mt can be calculated. This torque can be calculated, torque provided to this gear can be calculated later, which will be required when you estimate the module. Okay, now you see, the material of both pinion and gear is the same material. This is this information is important. Okay, you see, if their materials are same, okay, then all, see, one of them will be, when you design a pair of gear, you have to actually first decide the module. Okay, based on which one, actually you have to first decide which one you are going to design first. Okay, pinion or gear, and based on one of their design you have to decide the other one. Okay, now you see, module you have to calculate based on you have to actually first of all think, decide which one of them is weaker than the other. Okay, you see, when their materials are same, they are made of same material, then pinion is always the weaker one. We consider pinion is weaker than gear, so we design the pinion. Okay, so we design the pinion to be safe to withstand the load, and gear will automatically be safe. Okay, because pinion is weaker than gear, and since pinion is safe, now gear will automatically be safe. But if this condition is valid when pinion is always weaker when their materials are same. Okay, materials are same, but if their materials are different, then we'll have ultimate tensile strength, let's say 200 for pinion and ultimate tensile strength 300 for gear. Okay, then what we have to do is we have to find out something called the bending stress sigma b, which is normally SUT by 3. Okay, so this is 200 by 3, and this is your we'll calculate, keep it 200 by 3, and here sigma b for the gear, this is for pinion. Okay, we are given as for pinion, this is for gear, so sigma b is 300 by 300. Okay, so find out bending stresses for both the pinion and gear. Then you have to find out something called Lewis form factor. And this depends upon number of teeth in the pinion and gear. Lewis form factor for a pinion you find out, Lewis form factor for a gear you find out. I'll show you how to find out. Okay, so Lewis form factor multiplied by sigma b for pinion, you calculate after calculating Lewis form factor. Actually this you can get from data book, Lewis form factor, and this multiplied by sigma b for gear. Okay, now compare between them, whichever is lesser, that is the weaker one. Okay, so this is the case when their materials are different. Okay, but I normally prefer to give it a same material so that you don't get confused. So you have to design pinion if their materials are same. Okay, this information is required only when you cannot decide which one is weaker. Okay, now you see service factor is 1.3. Service factor is something which accounts for all these I can say external factors like vibration, some losses. Okay, some many losses and all. So that is actually used for, I mean, depending on severity of service, to you can say mild operation to severe operation. Okay, so that is something related to that. Now by assuming a pitch line velocity of 3.6, now pitch line velocity here you see this will have some I can say angular velocity, and it will have a pitch circle. Okay, the gears have pitch circle, pitch, pitch circle, which you please study yourself. Okay, and also it will be explaining kinematics of machines, right? So pitch, in the pitch circle, if we draw a tangent at any point, okay, and at that point we find the velocity, that is pitch circle radius multiplied by this omega. Okay, that is your pitch line velocity. Okay, here, and this pitch line velocity is 3.6 given to you, and the factor of safety also is given. So now these are the informations given to you, so you have to estimate the module according to beam strength. Now there are two type of actually design criteria, one is beam strength and one is wear strength. Okay, let me explain them quickly. Now you see this is one gear. Okay, I'm not drawing the complete gear, so this is one gear. Okay, now I mean this is the gear. Okay, now there's another gear which will be mating with this gear, and this tooth will push this tooth in at an angle like this. Okay, so this is one circle, this is called pitch circle for this gear. Let's say this is gear and that one is pinion. Okay, so pinion is driving the gear, so both the circle will touch at one point and there will have a tangent, and at that tangent this force makes an angle. Okay, and that is called pressure angle. Okay, alpha p also we write. Okay, this angle is pressure angle. Okay, now you see this force here actually will try to break this if this force is huge. Okay, then what we can actually, if we draw the free body diagram for this, then this tooth, the free body diagram for this one, this tooth. Okay, so if we draw like this, so you see the tooth, that tooth is connected here. Okay, this is a part of the gear, this part, see, this is connected here, right? I mean this is once, I mean solid connection is there, right? So this part is kind of free, and here we have applied a load, so you can consider like this. Okay, this is actually at an angle, I mean at an angle like this, so we'll consider there its say components. Okay, this one is alpha. So let's say this force is F, so this is F cos alpha, this is F sin alpha. Okay, so this force here is causing this one to, actually you can just consider like this can be considered equivalent to some cantilever beam. Okay, beam like this. So because you see one side is fixed, one side is free, so this is kind of cantilever beam, and here we have applied your some load. So this is actually, this may bend. Okay, bending failure is, you can say, possible here in this case. So we actually have to prevent the bending failure for this gear tooth. Okay, so if we can design that one, if we can design a safe diameter and how many number of teeth is required, okay, all these things, okay, so that it can withstand this type of failure, okay, then that is called your beam strength. Beam strength. Okay, right, whatever load you apply, okay, that is called P effective. So effective load is actually combination of all types of loads that you apply on this, and beam strength is actually given in newtons. That is a force that can be can be applied to this gear tooth, so that it just about to break, or you can say at that point its maximum strength is, let's say you just take a value 100 Newton. So this gear tooth can take up to 100 Newton, and if you apply more than that, then it will break like this, due to bending. Okay, so its bending strength here is 100 Newton, you can think, and P effective is the load that you have applied, okay, or externally applied, and it combination of all type of loads. Now if obviously if effective load, that is applied load, is less than beam strength, okay, beam strength, so it less than the strength, right, strength here is, it can take up to this one. So 100 Newton is your beam strength, let's say. So your applied load is, let's say, 90. So you can say this is safe. Okay, so your design is safe in this case. But if P effective load is greater than beam strength, okay, then your design is unsafe. Then what you have to do is, you have to actually re-estimate the module. You have to just take a different value of module, okay, then you have to recalculate everything, and then you have to check this criteria. Okay, you have to ultimately achieve this P effective less than beam strength, okay, which is something called design based on beam strength. Now another design is there, that is based on wear strength. Okay, now if suppose this gear tooth can withstand the beam, this kind of failure, but what happens, this gear tooth, okay, slides onto this one, okay, and wear takes place due to, let's say, unevenness of the surface, okay, surface of this gear tooth. And there's another gear tooth, although they are involute, okay, but after some time, after some operation, maybe they're working at a very high amount of you can say using impact loads. Many impact loads are there, okay, lubrication may not be proper, okay, high speeds are there, many things. So they may wear this surface, may actually slide over this one a little bit, and there is a possibility of wearing out, okay, of these surfaces. So just to prevent that one, we have to harden the surface of the gear. Okay, so there we consider the Brinell hardness number here. So we have to increase the Brinell hardness number. We'll check that thing. The higher the Brinell hardness number, the harder the surface of the gear. Okay, so that here Brinell hardness number is the criteria here for wear strength. Okay, so we have to actually we'll see how beam strength and wear strength are calculated. So Brinell hardness number gives you, the higher Brinell number gives you higher wear strength. Okay, so it is actually resistant to wear. Okay, right, like that. So now again, P effective load, if it is greater than wear strength, that means your applied load can wear it off. Okay, that suppose your wear strength is let's say 200 Newton, okay, but your applied load is 210 Newton. So you can say this means your gear will remain intact up to 200 Newton, or after that it will wear off. but your applied load is more than 200, so this will definitely wear off this one. So here also P effective should be less than wear strength. Okay, so this is something which is you have to take care of. Now depending upon which criteria you are using, okay, your design may be different. So in a question, let's say it is said that you check the safety criteria both from beam strength and wear strength point of view, then you have to check this criteria here for both of them. If only for beam strength is written, so you have to check for beam strength. We'll see how to calculate beam strength and wear strength. Okay, here you see now it is written that estimate the module according to beam strength and find the dimensions of standard proportions. Check whether the design is safe. Now it says that check according to beam strength only. Okay, now the next thing is second point, if the gears are machined to accuracy of grade 9, check whether the design is satisfactory from the standpoint of beam strength. Now the thing is, here you have to actually look at something called gear design at the beginning and gear design at the later stage. You see, when you design the gear at the beginning, okay, so just written somewhere. So what you have to do is you actually, you see, initial stages. Okay, at the initial stage, this P effective, okay, is calculated. Okay, this P effective is calculated by using this formula. P effective equals to CS. This is surface vector divided by velocity vector multiplied by PT. This is the tangential force that I have said. This one. Okay, this tangential force, and this is the normal force. After resolving, we'll get this tangential force and normal force. Okay, normal force is cancelled out. Okay, and but this tangential force remains. This is PT here. This PT multiplied by 2 factors is your effective load. Okay, this one. And this is for the beginning part, initial part. If you are interested in tolerances, okay, gear tolerances, then that is the final stage of design of gear. Okay, and there what you have to do is the effective load has to be calculated using this formula. Okay, and here you see CS divided by CV is not considered, but instead we have to add something called PD, and this is called actually incremental dynamic load. This is called incremental dynamic load. The PD is called incremental dynamic load. Understood? And that is given by this formula. Okay, and this formula again, here you have few terms, K3V. V is actually pitch line velocity again. Okay, which is corrected. That means I mean, if you assume it and you have to calculate everything, then again you have to recalculate it, and then that is called corrected. And K3 value is given in SI units. Okay, C is a constant, and that is can be found by this formula, and C again is equal to E small e. This is error. This is called error, divided by K1 into 1 by E1 plus 1 by E2. Now E1 and E2, these are your modulus of elasticity for pinion or gear. Okay, E1 is for pinion, E2 is for gear. K1 again for this 14.5 full depth, 20 degree full depth is given. So we normally have 20 degree full depth, so K1 value is 9. Okay, so E1 and E2 will be given to you in the question itself. Okay, maybe it is yeah. So in this question, I think it is given somewhere. Actually it is not given, but actually the value is written here. I missed that one. It is given here itself. Here you see E1 and E2 made of steel. So actually take E is equal to 206,000. Okay, this has to be given. Okay, or in some data book it can be found, but if you do not have it, you have to take it for steel. Okay, now what you have to do here is, you know this PT, right? You know CS also, but you have to calculate PD somehow. So here you see, now you can calculate C if you know only this small e, okay, and b here is actually your face width, that is 10 times the module in general, and pt is again known, v is known, k3 is known, c has to be calculated, then only you can calculate pd, and c can be calculated using this formula. So here you have to calculate small e. Again small e is called the error, and error has to be calculated used by this formula. So total error, e is the total error for, actually that is a combination of error for both the gears. So here actually you are considering, you are precisely calculating the gears using the tolerances. So here error for pinion and error for gear has to be calculated separately. And again formula to calculate this error e, okay, is this one. You see, okay, this not written. Actually this formula is different for different tolerance grades. So we have a tolerance grade table here. So grade 1, grade 2, 3, 4, like that. Okay, we have something like this. Okay, so grade 9 is not included. Actually grade 9 is here. For grade 9, let me write the formula here. Actually it is available in the textbook. This table is not available in your data book. Okay, for grade 9 it is m plus 0.25. Sorry, 22 plus 1.85. okay, so this is for grade 9. This is 22.00 plus 1.85. so this is actually required. So you plus I'll share this table with you. Okay, so this you have to take from the table. Okay, now for any grade, error grade, it will be given in your question. So which error grade is required, you have to look from your question, and for that particular, let's say it is written design the gears for an accuracy of grade 3. So then grade 3 you have to take, and this will be your relation. And here one unknown is there, it is phi. Okay, that phi can be calculated from this relation. See, so many calculations inside this PD. So this 3 here, phi can be calculated again using from this formula. This is module plus 0.25 into root over d. Now phi for pinion has to be calculated, and phi for gear has to be calculated, because phi p will be module is same for gear and pinion, so we don't write mp or mg. Okay, for all the gears that are mating perfectly, so module has to be same for them, so m only, plus 0.25. this is for pinion, so we have to use diameter of pinion. Okay, so if you have to find out phi g, then module plus 0.25 root over dg. Okay, so using this you find find out phi p and phi z. Then for grade 3, let's say your question is there, so for ep will be 2 plus 0.16 phi p, so that is for pinion, and ez will be 2 plus 0.16 pi z. Okay, so ep will be for grade 3. For grade 3 we are writing, for grade 3 is a relation 2 plus 0.16 pi, no, 2 plus 0.16 pi. So this is p, so this will be p, so ez will be 2 plus 0.16 pi z. Okay, so we will get ep and ez, add them to get total error e. Okay, and then you will put here to calculate c, and then you will put here c to calculate the incremental dynamic load. Okay, and then you will put it here to calculate your p effective. Okay, so this is the process of calculating p effective. P effective at the beginning, if it is in your question it is not given that no information is given about the accuracy of grade 3, 4, 5, 6, 7, 8, 9, something like that, then no need to do this. Okay, this extra calculations, p effective and all. But if it is given, then you have to do this. Okay, according to that accuracy given. Okay, so effective load is this one, right? Okay, but otherwise you have to do up to this only. Okay, now this is for effective load. Now you have to find out beam strength, wear strength, if it is given in the question. Okay, now what else is given in the question is, you see, you have to find the Brinell hardness number if wear strength is same as beam strength. Okay, all right, now you see Brinell hardness number, wear strength is same as beam strength, means you have to first find out beam strength and equate it to wear strength, okay, and then you have to find out a Brinell hardness number from there. Now let us look at how to first estimate the module, okay, and then according to beam strength find the your standard proportions. One more thing I have to tell you, that formula to calculate the module, okay, this one, okay, according to beam strength, this is the relation, okay. So this is when the your load is static, okay, static load, okay. So it is written in the question. So if the load is static, then you have to use this relation, okay, but when the load is fluctuating in most of the cases, then you have to use this relation, okay. So this relation is available in the data book, okay, and this relation you have to use in the cases when you see, like when your load is fluctuating, okay. It is in this case, let's say, how do I'll give an example, okay, just a moment. Okay, just wait. Okay, for this example, okay, this material is given to you. The material for both the gears is C40 steel, okay. This is another example. I will come to this. Here you see, you do not know the value of your bending strength, okay, bending stress. So here what you have to do is, you have to look at your data book, okay, and you have to find out something reliable static stress from your data book. This is available, okay, in the data book, and for C40 steel this is the value. So here this is static stress, and you are using this in your calculation. So you have to actually take the module formula, this one, okay, this one, to calculate, right? But in general we use this formula, okay, whenever. So you can just see, whenever this your value of your ultimate tensile strength and this is given, okay, then you use, or if nothing is given, okay, then you use this one, okay, this module formula, okay, this one. All right. So for this the particular problem only, okay, I'll let me I'll come to that problem, then I'll show you the data book, okay. But we will be using this when most of the cases. This is the formula for module to be this is calculated based on beam strength, okay, beam strength, and based on wear strength we have another relation, okay, of module. It is actually based on wear strength. So this is the relation, okay, based on wear strength. So just the difference is there, small difference, ZP square is there, okay, and Q and K are there, okay, and here some little bit of difference is there. Here some formula, from that formula Zn is there, here n is not there, n is there, sorry, Z square is there, and Cp is not there, Cp is there, and then this one Q and K is different actually. See, this is, here we have y is your least form factor, okay. So let me just start your explain this numerical here. See, these are the given things, okay. Now we have to use this relation, okay. Least form factor can be calculated using this relation. Y, capital Y, is equal to pi into small y, okay. So from table 12.5, value of tooth form factor at tip. So now see, table 12.5 here is 201. So here this is the table 2.5 to find out values of tooth form factor, least form factor, okay. So tooth form factor is small y, and if you multiply pi with this one, then you will get least form factor, okay. So you see, you have to actually you have to find out this y, okay, from this table based on this number of teeth. Z is the number of teeth here. So we are designing for pinion. Since their materials are same, so pinion will be the weaker one, so we design for pinion. So in the question it is given that your number of teeth is 18 for the pinion, so 18 here, okay, is for the pinion. Now your this y have to be calculated for 20 degree full depth. So full depth involute, actually it is not written, so I mean involute, so this is 20 degree full depth only, this part, okay. So 20 degree full depth, so it is not written involute, no problem. So this is 20 degree full depth, this is stub, okay. So 20 degree stub we are not considering, or 42.5 degree full depth also we are not considering. So 20 degree full depth for 18, the value of y is 0.098, okay. So that is small y is 0.098, and multiply this with pi to get capital Y. This Lewis form factor is 0.308, okay. Lewis form factor is required later, okay, when you calculate module. Now see, this is velocity factor. Now see, velocity factor again from a relation that is called Barth's, B-A-R-T-H, Barth's relation, okay. So here this one. So for ordinarily cut gears, I mean whatever, just have a look at this velocity, pitch line velocity up to 8 meter per second, okay. You have to use this relation, okay. So pitch line velocity which is up to 13 meter per second, then you have to use this. Here it is carefully cut, and here it is ordinarily cut, okay. So if I mean in general we take this one, okay, ordinarily cut gears to design at the beginning stage, okay. So and this is for very accurately cut, and that is between 6 meter per second to 20 meter per second, okay. So just have a look at this one, okay. If it is if it is up to 8, then you use the formula. If it is greater than 8, then you use this formula, okay, like that, okay. Now actually this depends upon the designer, okay, and what type of gears he wants to design. Then he will select the velocity factors relations from this, and then you will put the pitch line velocity here, and then he will calculate your velocity factor. Now since it is less than it is given as 3.6 meter per second, so we'll use this relation. So here you put, and you'll get CV, okay. CS is given. Now you have to estimate the, first of all you have to calculate the module, calculate it using the formula, okay. So kilowatt is your power, okay, power in kilowatt. CS is your service factor, FS is factor of safety, this 16/6, this is pi. ZP, because you are designing the pinion, so we'll have to put ZP, and P for pinion we are calculating. So ZP, that is your number of teeth in pinion, that is 18. Speed of pinion, that is 800 rpm. CV have just calculated. B by M is the ratio of face width divided by module. So this is module only, this is module, this is also module, okay, but this ratio is given as 10. So B is 10 times the module. So here if you put 10 into M, so MM gets cancelled out, so here we'll have 10, okay. So SUT by 3 is your bending strength. So SUT is given in your question. So this is 200 by your 600 by 3, this is 200, and Lewis form factor Y is this one that you have calculated, okay, whole to the power 1 by 3. So you calculate this one, so you'll get a value of 4.18, okay. Now this is the calculation of module, but you have to take the module from your data book, okay. So here we have recommended series of modules, right, and here what you have to do, you have to look at this preferred, that is first column, choice 2 second column, choice 3 third column. Again this is continuation, okay. So what is actually you have to look for, you have to actually first calculate the module. Here we have got 4.18, okay, but you have to take a nearest value of module from this table. So here you see 4.18 is your value, so you have to always go for preferred column first. So search for a nearest value of 4.18. see 3 and 4, okay. 4.18 is more near to 4, okay, then 5, right. So we have to actually choose between 4 and 5, right. We cannot take 3 here, so we have to take either 4 or 5. generally, okay, it is recommended you take a value higher than your calculated value. Now 4.18 is your calculated value, you should take 5, okay, but you can try 4 also, not a problem. And you can try 4 and you can get ultimately at the end, if you get your design is unsafe, then what you have to do is you have to take the higher module. Okay, suppose by taking 5 also your design is not safe, then you have to take the next module 6. Okay, then you have to recalculate everything. That's why gear numericals are a little bit trickier. Okay, so let's see. Anyway, so here 4.18 is your calculated value, so you have to take your you have to select your module as 5. Okay, 5 here. All right, so this is called selected modulus 5 from preferred value table to 0.2. Okay, so once you get this, so what you can do is later you can find the standard proportion dimensions. So diameter of pinion, which is, you see, module is equal to diameter by z, okay, d by z. So for pinion, module into your number of teeth. So for pinion, tp, diameter of pinion is this one. So finding this one, we get 90. Number of teeth, this one. Number of gear, diameter of gear, this one. And other remaining standard proportions can be found from this. Okay, here standard tooth proportions for involute. If you want to find addendum, then using this one, use module. Okay, this is based on diametral pitch, this is based on diameter circular pitch, this is just based on diameter pitch, this is based on module. Use this column here to calculate anything you want. So if you want to calculate addendum, this is directly equal to module. If you want to calculate the addendum, then this is multiplied 1.25 multiplied by the module. Okay, so your module is 5 now, so 1.25 multiplied by 5. So similar to thickness can be found by multiplying 1.5708 multiplied by that module, that is 5. So 5 into that one. So everything will be calculated using this one. So that's why data book can be used here to calculate these standard tooth proportions. Okay, so although it is I mean not actually mentioned, it's not clarified in some questions that how many tooth proportions you have to calculate. So it's up to you. Okay, you can calculate 3 or 4. Okay, that is not a, I mean, if it is asked in the question, calculate addendum, tooth thickness, tooth space, everything, then you have to calculate all those. Okay, so now yeah, you have estimated the module. Now what you have to do is you have to check for safety. Okay, that I have explained. Okay, you have to check whether P effective is greater or less than beam strength. Okay, for that you have to find out what P effective. So P effective, for before that you have to find out, let me write it down. So now you have to find out P effective. So P effective can be found out by CS by CV into PT. Okay, first for the initial stages. Now PT has to be found out. PT can be calculated, tangential force is 2 times your MT, okay, that is your torque divided by your D, diameter. Okay, so now you are designing for pinion, right? Everything you are designing for pinion, so you have to take the your diameter for the pinion. Okay, you are designing for pinion, that's why you consider it as pinion, and this torque is again supplied to the pinion. So this for torque you have to find out first. So torque can be found out by power divided by omega. Okay, so here you see power divided by omega is 2 pi n. 60 was there, so 60 will go above and multiply by 10 to the power 6 just to reduce it to Newton into millimeter. Okay, so like that. So this relation you can also just like by power is given as around what is the power, 6 kilowatt. So you can 6 into 10 to the power 3, you can write like this. So 2 pi n is 800 by 60. So now this is in Newton into meter. Okay, you will get whatever you get here is Newton to meter. You have to again multiply 10 to the power 3 to get Newton into millimeter. So that's why this is 10 to the power 6 is already written here, so that you can directly put the value of power in kilowatt here. Directly put 6. Okay, 10 to the power 6 is already there, so that you get Newton into millimeter. Okay, now tangential force. Now once you get this torque, so you put it here, and diameter is already known for pinion, you calculate PT. Now you see pitch line velocity now has to be corrected, because why? Because your module actually calculated value of module is 4.18, but you have estimated it, you have taken it as 5. So your design this factor CV has to change actually in this case. So using that one, this module, you have calculated the diameter as 90, otherwise it would have been your this is module multiplied by your z. Okay, so this is 18, so it will be less than 90, but you have taken it diameter, you have increased the diameter, so your velocity will like again change in that case. So that's why you have to correct the velocity factor, okay, CV. So for that, you have to first find out the corrected pitch line velocity. So pitch line velocity is nothing but this one, that is pi d. That means velocity here is equal to, you see, r into omega, right? So r multiplied by 2 pi n by 60. Okay, right. So here you see, here you can write like twice r multiplied by pi n by 60, and which is twice r means 2 times radius is diameter, so d into, we just rearrange pi d n by 60. So using this formula you can actually find out your velocity. So this is for pinion you are doing, so n dp np, so here dp and np, okay, are written here. Okay, fine, all right. So what you now can actually, here you see, okay, you have found out this pitch line velocity. Okay, now correct velocity factor. Now this is modified, so find out the CV value, corrected one. So then effective load is nothing but CS, that is your service factor divided by velocity factor multiplied by PT. Okay, so this is the relation. So 1.3, this is 4.1, this is value is we have calculated PT, so this is P effective. Now we have P effective. Now this is the formula to calculate the beam strength. Okay, beam strength SB is module multiplied by face width multiplied by bending stress multiplied by Lewis form factor. This multiplication of all four are is together known as beam strength, and this is beam strength SB is equal to, now you put module as 5, B is 50. Okay, that is 10 times module, so B is 10 into module, so 10 into 5, that is 50. Okay, so sigma B is 600 by 3, it is SUT by 3. Okay, here in general we take it as sigma B as SUT by 3. Okay, so this is ultimate strength by 3 multiplied by Y is 0.308. Okay, so which is 15,400. Okay, this is beam strength. Now obviously your beam strength is much larger than your effective load that you have applied, right? So your strength is higher, so your design is safe. Okay, that means it may due that tooth may break like a beam. Okay, bend due to bending. Okay, if it reaches 15,400, but it is much lesser than that, so SB is greater than P effective, so design is safe here. Understood? So this is the second part answer. Third part is for grade 9. Now here it is written as for grade 9 you have to calculate the error. Okay, because in your question it is written that if the gears are machined to accuracy of grade 9, check whether design is satisfactory from standpoint of beam strength. Now you have to design the gear precisely. Okay, I mean using the later stress calculation. That means again you have to calculate P effective, but using CS PT by plus PD. Now you have to calculate PD. CS is known, PT is known, PD has to be found out. Okay, and beam strength is also known. So again you have to first only find out P effective, again separately using this formula, because error is given, error for grade 9 is written here. So use those relations to calculate PD now. Okay, now you see for grade 9 again, or is for grade 9 the error relation is this 22.18 into 5. So phi can be found out using this relation. Now for pinion, phi p is m in this one, so dp is known, so this is the diameter of the pinion which is after putting it we get phi p. Okay, again for now after getting phi p we can find out the error for pinion. Okay, ep is equal to this one. This is in micrometer, you remember this one. Error here is in micrometer, which is also written in your micron or micrometer is the same thing. Okay, this is micron or micrometer. So micrometer is, you see, that is 10 to the power minus 3. Okay, so millimeter less than that 10 to the minus 3 micrometer. Okay, so 10 to the minus 6 will be nanometer, sorry, 10 to the minus 9 will be nanometer, because 3 into 3 is 9. Sorry, so here minus 9 will be nanometer. So before that we have micrometer, then we have millimeter, then we will go above. So 10 to the power minus 3 millimeter is equal to 1 micrometer, mu-m. Okay, so this is in micrometer, remember that, because you have to take it to millimeter later. For gear, again this is the relation. I mean, this relation is same, but you have to use phi g, and here in if you are writing z here also it will be z. So diameter of the gear, you put it there, then you get phi g. Then error for the gear you calculate using this one. So this is 40.54 micrometer. Total error, addition of both of them, so we will get 75.806 micrometer. Then this micrometer is converted to millimeter by multiplication by minus 3. So this is the total error. Now we get E, so we can find out what? C. Okay, C, capital C. Okay, because this is the relation that you have to use to find out the incremental load. So E is known now, K1 is known. For 20 degree full depth, this is 9, and this is given. Since both are made of steel, both have the same material, so their modulus for elasticity will also be same. So this is 206,000 Newton per meter square. So put them here. So calculate C. C is around 867. So Newton into millimeter, not millimeter square. So now put this value of C here. Okay, B is 10 times module, PT is known, K3 is generally 20.67 in SI unit. K3 is also known, V is also known. V is the pitch line velocity. Okay, now you see this is the incremental load after putting all the values. 20.6, this is this one, and here this is root over of, this is addition, this plus this root over. After calculating that, we get PDS 12,084.31. okay, this is very huge amount of incremental load. Okay, now after you see putting this PD here and CS multiplied by PT, we get P effective as 14,153.312 Newton. Okay, now your beam strength here is, you see, 15,400, right? And you have designing the gear for accuracy of grade 9, your P effective becomes 14,153. Still it is less than your beam strength, so design is against safe from beam strength point of view, beam strength standpoint. Okay, finally it is given in the question that find the Brinell hardness number if wear strength is same as beam strength. Okay, so you see, now you equate wear strength and beam strength. Now wear strength formula is B into Q into D into K. Okay, Q is actually called a ratio factor, and K is a factor which is, for steels it is generally 0.16 multiplied by BH and Brinell hardness number divided by 100 square. Okay, so these are the, this is K. Okay, so this is the relation. So Q is ratio factor here, you see, that is 2 into your teeth, number of teeth for gear divided by number of teeth for pinion plus number of teeth for gear. Okay, which is Q, right? Okay, now for pinion, now you are designing for pinion obviously. Okay, so this is, they equate them to beam strengths. Now beam strength is known, that is 15,400. so this is BQ dP into K is 15,400. dP is known, that is diameter of, for pinion you are designing, so that's why you put dP here. Okay, now this is actually, this ratio factor will change if your gears are internal gears. Okay, now for external gears, both are connected like this, in this manner, so that is your external gear. And if one gear is inside another gear, that is called internal gear. Okay, you don't have to worry about that. So this is the ratio factor here, so which is 2 into, this is ZG is 90 and ZG is 90 here, plus ZP is 18. Okay, so from here you can calculate your Q value. Okay, now K equal to 15,400 divided by this one. You see, actually K only you have to find out because you need the Brinell hardness number. B is known, that is 10 times the module. Okay, Q is given, diameter of pinion is known. Okay, so this is already given here. So K can be found out by 15,400 divided by P into Q into dP. Okay, using that. So K is equal to 0.16. This is the relation for now. Once you get K, there is another relation for K. Okay, K can be found for steel gears made of steel, BHN divided by 100 square. It is the in general relation. Okay, so this is not valid for all type of gears. So for steel gears, this is the relation. Now from here you can calculate the Brinell hardness number by putting the value of K here and calculating for this. This is the Brinell hardness number for the gear. Okay, so this was all about a gear numerical, first gear numerical. Now we'll move to the second gear numerical. Okay, that I'll just show you in your data book. Okay, so look at this. So this one. Okay, so gear numericals are similar, but for this numerical, this particular numerical, you have to actually take the value of your static stress from the data book, because this is given as only the designation is given. Okay, 20 degree full depth spar gear is there. Okay, number of TTS pinion is 18. Okay, fine. Velocity is 4 or 4:1 is same. Pinion is driven by this one, so pinion here is material is for both the gears is same, so here pinion is the weaker one. Okay, gear velocity 10 times the module. Okay, considering initial pitch velocity of 8.5. now the thing is actually this 8.5, initially it was actually I have written as 5.5 because this one and the thing is the relation we had to use it's this one. Okay, 3.05 divided by 3.05 plus P. Okay, but by mistake this relation was used. Okay, 4.58 divided by 4.58 plus P. So this is valid for speed higher than your actually higher than this one 8. Okay, that's why this is written as 8.5. Okay, so there's a mistake in calculation, but I'll just explain the processes here. Okay, procedure. So considering initial pitch slump velocity of 8.5, estimate the module and determine pitch cycle diameter, that is dP and dz, and then dynamic to thickness. Okay, now first of all for C40 steel, these are the informations given. So now we have to first of all look at the data book. Okay, and search for the property of C40 steel. Okay, now look at this here, table 12.7 your page 234. So page 234 table 12.7, here you will get allowable static stress for in use for Lewis formula. Now for grade C40 steel, steel C40 untreated, here it is written. Okay, for that you have a value, that is allowable static stress. Okay, sigma d, that is 207 meganewton per meter square. Okay, so this value you have to take, and this for this type of problem only we have to use the module formula here like this, because the static stress has been used here. Okay, like that, sigma d. Otherwise we will use the module based on beam strength. Okay, now you see this is allowable static stress 207 meganewton per millimeter square, which is nothing but 207 newton per millimeter square only. Okay, if you calculate, then you will get this, right? So from here you get the torque from this relation, power equal to torque into angular velocity. From here power is 12 kilowatt, so we have found like this. So we have got 79.6 newton meter, so multiplied by 10 to the power 3 we will get 79,577.47 newton millimeter. This is your torque. Okay, now what else we need in this relation? We actually need torque, we need your this one allowable static stress. Okay, so we have we need CV, we need a factor K, and then we need this least form factor and ZP. Okay, K is actually nothing but B by M. Here it is written as K. Actually in this relation, this relation is available in data book. Okay, this one here, say least equation for beam strength of tooth M equal to 2mt divided by sigma d Cv K yz, and K is equal to B by M. Okay, B by M. So that is B by M only. So this is given as face width is 10 times the module, so B by M is 10 only. Okay, so K is known, Y least form factor is has to be calculated, ZP, that is number of teeth in pinion, this is given. So MT you have found, sigma d you have found, so K is known, CV you have to find out, and least form factor you have to find out. So first you find out least form factor. Again from that table that I have shown, for 18 teeth you find out small y, okay, that is 0.09, and multiply pi with that to get the least form factor, that is capital Y, this is 0.3078. okay, now pitch line velocity 8.5. Actually you should use this formula, 4.58 divided by 4.5 plus V. This is actually by mistake written as 5.5, and the calculation mistake is also there. Yes, so this will be 4.58 divided by 4.58 plus 8.5, and this will change. Okay, CV will change, and this CV value has to be corrected here. Okay, like that. So we'll get a different value of module. Okay, we'll look into that, but this is the mistake, calculation mistake is there. So we'll actually you can rectify and you can just calculate correctly the module. You see, after getting this value of CV, then you put it here, everything you put it in the formula, then you get the module 3.13. now you have to estimate the module, okay, from table 12.2 page 229. so here page 229, table 12.2, 3.13 is your value, so take it higher than 3. So this is 3.3 and 4 are the values which are preferable values. Okay, so you do not take 3 is less than 3.18, so your design may not be safe. They take a higher value, this is 4. Okay, so you have estimated it as 4 modulus 4 mm. Okay, now from velocity ratio we can actually get this your number of teeth in gear. So velocity ratio which is positive, it is higher, that is 4. so that I have told you that you can, if you do not remember, you can write this relation somewhere. If it is higher than 1, then this is dg by dp. If it is lower than 1, that is 1 by 4, let's say that will be dp by dg, so time, or zg by zp, similar thing. So here it is higher than 1, so zg by zp will be the relation. So number of teeth in gear, number of teeth in pinion. Okay, because obviously you can also by intuition also you can think like more number of teeth will be there in the gear and less number of teeth will be there in the pinion. So when this is more, this is less, so this will be obviously less than 1, so greater than 1, the ratio. That's why this is zg by zp. Okay, so from here zg you can find out, it is 72. Pitch circle diameter is this one. Okay, so zg and zg, dp and zp, this one you can find out now. So addendum is required, so addendum is directly equal to module. The addendum is this one, two thicknesses this one. Okay, so you can calculate everything by using the relations that is given in the data book. Okay, so next numerical is similar actually, which is given to you here, but here actually you know that this value is actually not given in the least form factor table. That's why we had to interpolate here. Okay, and in general in your exam, okay, this thing will be given to you. Okay, and but if it is not given, you have to follow this process. I mean this numerical is actually solved in the similar manner, just this one was not available, 72 number of teeth, so that's why you have to interpret. And this one actually, this problem is where the materials are different actually for pinion and gear, so we have to find out their cross product of bending stress multiplied by your least form factor. That's why we had to determine least form factor for both of them. So you see, this is for pinion 54, for gear it is less than 54. So here gear is weaker. Okay, gear is weaker than pinion, so we have to design the gear here, not the pinion. Okay, and rest of the things are same. So it is 5, so this we are using this one. So this relation again, okay, this relation here again. Okay, in the data book this is estimated near to the, so m is 4. Okay, so here you see beam strength is this one we have got. Okay, and from the relation, from this power relation, we get the torque, we get the tensile force PT, and then we get the P effective. Now see, P effective is much higher than your beam strength. Okay, that means design is unsafe. Design is not safe here. This is not safe. We have to re-estimate the module. What you have to do is you have to take another module now, which is not shown here. Okay, but you have to do that. You have to take the higher value of module, then you have to recalculate everything. Now it will be 5, this will be 50, and this other things will also change. Here also it will change. Okay, module here also will change. So then you have to recalculate again. Okay, then based on module also your CV will also change. Then if you have to check whether it is safe or not. If it is not safe, again you take a higher value of module, again you redesign everything you have to do. Okay, so that has to be done. So that's why this was just an example, and you have to do up to, if it is unsafe also, okay, just finish your numerical up to this. Okay, safe or unsafe, that is what is asked in this question. Okay, so if it is not safe, then it will write down this, you need to re-estimate the module. Okay, re-estimating the module, take a higher value of module, and again recalculate everything. Okay, like that. So these are all about your gear numericals. Okay, next we'll talk about your numericals for your bearing. Okay, thank you.